Welcome, everyone, and welcome to our 50th session of the Inspiration Exchange. We're really excited to mark this milestone with today's discussion on autoformalism. And thank you to all the speakers and panelists and everyone joining us today. My name is Marika, and I'll be your host. And today's session will be split into the usual two parts, with the first presentations from Tennison Liu, a final year PhD student from the Schaar Lab, alongside with Professor Yuanzhang Xiao, also a Schaar Lab alumnus and current associate professor at the University of Hawaii, both leading researchers in this new world of autoformalism. And then second, we have the roundtable and Q&A, where we're joined by Professor Radek and Professor Stefan. I'll be giving a short introduction of them before we start the panel. But with that, we'll get this presentation started. So I'll hand it over to Tennison.
So thanks everyone for joining this session. And thanks, Marika, for the great introduction. So my name is Tennison, and I'll be giving a talk on autoformulation for decision intelligence. And the work in this talk was done jointly with Nicholas Astorga, who's also a PhD student in the lab, as well as collaboration with Professor Xiao, who you'll hear from later, and with supervisor Professor Van der Schaar. Cool. So to set things up a little bit, I want to briefly talk about what decision intelligence really is. And simply put, it's about making an optimized decision in sort of business or everyday scenarios. And oftentimes, when we think about the optimal decision making, there is a prescriptive modeling step. And what that really means is that given some sort of real world problem that implicitly contains some objectives, some decisions that have to be made, and some hard constraints, there's a step where you translate that into a mathematical model or a prescriptive model that could be based on some mathematical frameworks, could be based on machine learning. And once you solve that model, you can get an outcome which tells you what decision you should make that is relatively optimal. And decision intelligence really comes up almost everywhere we look. And here I've shown some pretty well-known examples, one of which is portfolio optimization, where you want to maximize your returns while minimize some sort of risk boundaries. It also comes up in work assignment or resource allocation, as well as with scheduling and planning, where you want to allocate resources and human capital over time to accomplish some sort of outcome. While this is all sort of, well, these sort of decisions and modeling come up almost everywhere, it is still a very expertise bottleneck process. And what that means is that it is a very, very manual modeling procedure. It is costly, and it is also very heavily expert driven. And autoformulation really is about the idea of whether we can use advances in machine learning and exploit these opportunities to automate this modeling process, to go from some sort of problem directly to a decision, an optimal decision that we can make. And the idea is that this will reduce the time and expertise barriers, enable faster experimentation to build better models, and focus time and expertise on more useful endeavors, as well as democratize access of these tools to people who might not be optimization experts. And I've shown a quote here from Werner Vandenberg's textbook, which sort of communicates this idea that really, when it comes to optimization, the modeling is one of the most important things, because with the advances in solvers and technologies, once you have a model in many settings, actually obtaining a solution or obtaining a decision is quite straightforward. And I think I just also wanted to illustrate this with a bit of a real world example. So we start with some sort of problem that we care about. And a nice example of this is maybe allocating beds in a hospital, where you want to make sure that you're maximizing patient outcomes while also minimizing whatever cost or resource constraints that you have. And essentially what autoformulation is you go from this problem to some sort of model. And in this case, this is a pretty straightforward linear program where there are some objectives and some constraints. And then you can sort of also translate this into a computational model that can then be passed to very advanced solvers that can give you the sort of optimal allocation here. And many of you might be wondering, so if this is the case, do large language models work, and these frontier large language models just work on these type of problems? And in our experience and our experimentation, the answer is not really. And in general, like frontier LLMs, including some of the latest reasoning models, cannot correctly formulate optimization programs from scratch. And there are two main reasons to this, one of which is that they don't really use tools that can drastically improve auto formulation. And many such tools have been developed, can be used to partially evaluate different types of model hypotheses and also improve the efficiency of the modeling process. And the other factor there is that they struggle to systematically search the space of possible models. And what that appears as is sampling a lot of redundant models that are very similar, ignoring areas of the modeling space, or essentially ignoring different types of modeling approaches completely and failing to come up with very novel or useful model solutions. And so that sort of hopefully sets up a nice sort of context and background. And I wanted to highlight some of the work that our lab has been doing in this space. And today I'll be talking mainly about the first one, where we focus very sort of closely on mathematical optimization. And later on, Professor Xiao, he'll be talking about formulating models for sequential decision making. And he also sort of addresses the concern of how do you make the model easier to solve. And more generally, there was a recent work as well, which generalizes beyond mathematical optimization. And it looks at all these different types of approaches for combinatorial optimization problems that include meta-heuristics and heuristic decision making. But yeah, and just to recap, and some of these things I've already touched on, when it comes to building models to make better decisions, so one of the key challenges is that you have this very large set of possibilities of different types of models that you can make. And to be able to efficiently search through the space of possible hypotheses, you have to navigate uncertainty, which is at each step of the process, it is unclear what formulation or what modeling decision will lead to a better model overall. And there's also a high degree of redundancy. And redundancy here just means you can have many different models that appear different, but are actually the same mathematical objects underneath. And the reason why redundancy is a big problem is that you spend a lot of effort, essentially, especially with large language models, they spend a lot of effort evaluating mathematical objects that are exactly the same, that don't give you any additional information in principle. And the third challenge is, how do you evaluate that a model is formulated correctly? And to make this a little bit more concrete, so say you have a problem and you've come up with a model and you're pretty happy with the model, and you pass it to a solver, and the solver says, great, this model is pretty good, it's feasible, and it gave an optimal solution, a globally optimal solution. And you might be pretty happy with that, but then the model itself might have neglected a very important real-world constraint. So the fact that the model itself gave you an outcome does not actually mean that it correctly and faithfully represents all the requirements of the problem that you actually trying to solve. And next, I'll be talking a little, so I'll be moving into the method description now. And I wanted to start with a high-level conceptualization, which is that you can think of auto-formulation as a two-stage search process or an exploration process over the model space. And essentially, there's, to be explicit about it, there's one transformation from a description of a problem to a mathematical formulation. And then there's a second process which goes from the mathematical formulation to a computational representation, which you can then, it's ready for the solver, and you can call a solver, and then you can get an outcome. And the objective of the search process is to maximize some evaluation measure, which we denote as Q. And Q can represent and encode a lot of things, but most fundamentally, it can encode formulation correctness, which is what I mentioned before about whether a model correctly represents the problem. And then after that, you can think about whether there are ways to make a model that can give me an optimal decision, and whether there are ways to make models that can be solved much faster. And I just wanted to sort of emphasize the scope again. And in this work that I'll be presenting, we consider only mathematical optimization models. And mathematical optimization models are those that can be written in the standard form shown here, where you have some decision variables x and you have some objective function f defined on top of x. And the optimization process is subject to certain constraints. And here, these are shown as systems of inequality and equality constraints. And in this special case, how we approach autoformulation is as a hierarchical exploration process. And I'll talk about how the hierarchy emerges in a little bit. But at a high level, we utilize large language models to do model generation as well as model evaluation. And the exploration process is done through a Monte Carlo tree search, which is a structured exploration policy. And we also utilize many types of symbolic solvers that can help us improve the efficiency of the search and also to provide feedback to guide the search direction. So the hierarchy within sort of these mathematical optimization models, for those who work with these quite regularly, will be pretty obvious. And you can think about a model as containing 4 components. And essentially, in the first component, which is denoted M subscript 1, you identify the parameters and you formulate the decision variables, which are the quantities that you want to optimize. And based on that, you can then come up with objective functions, and then equality and inequality constraints. And throughout the modeling process, you can kind of think about it as for each component, you're building on a partially complete model. And here, a partial model, for example, is if you already have the decision variables and objective function, then we can think about formulating constraints. So it's like this incremental model building process. And how we exploit that structure is by using a pretty classical technique, which is known as Monte Carlo tree search. And with any sort of Monte Carlo tree search algorithm, there are essentially 4 components. There's a selection step. So the selection step is given the tree. And here, maybe I should talk about what the tree represents. So previously, I said there were 4 components. And you can kind of think about each level in the tree as corresponding to one of these components. So there, in our case, the tree is exactly depth 4. So the first layer would be decision variables and objective functions. And as you go down, each layer represents one of these components. And selection here is just about, given the partial tree that you have at a particular iteration, how do you select the most promising branch through this tree, which represents one modeling approach to explore further. And once you've selected that branch, then it's an expansion step. And an expansion step is basically, now that we have this branch through the model space, let's add another component to it, right? And for example, if you already have your objective functions, equality constraints, now let's add the set of inequality constraints. And once you've added something, then the next step is evaluation, which is about how obtaining some sort of reward signal on how good that model actually is. And once you have that signal, then there's a 4th step, which is known as backpropagation, which is essentially just updating the statistics up through the branch so that all the nodes in the tree that are involved in this path have new value updates. And I'll talk about some of these steps in a little bit more detail. So I'll start with expansion. And with expansion, what we really want is for the large language model to generate diverse candidate components. And essentially how that goes is that given we're at a certain depth in the tree and we have a corresponding partial model that we've selected, we can generate a set of candidate components that can be added incrementally to the model. And the second step is we use these tools known as SMT solvers that can, in certain sort of mathematical cases, tell us if 2 equations or sets of equations are equivalent. And that allows us to remove the ones that are functionally the same. And having done that, we do the 3rd step, which is for each possible candidate, we try to estimate which one of them is likely to be better. And this evaluation step is largely focused on semantic correctness. And semantic correctness is essentially whether the model correctly reflects the requirements of the problem. So, and this is done using two reward signals, one of which is a signal from the solver itself. And this signal is about whether the model itself is well formed, whether it is solvable, whether it's feasible. And then the second part is utilizing an LLM to do a comparative evaluation, which is anchored by the problem that we're trying to solve. Which of these candidate models more accurately represents the actual decisions that have to be made? The other two components, namely selection and backpropagation, are relatively more standard mechanisms, and selection is performed using the UCT policy, and that stands for upper confidence band on trees, which is a decision-making strategy where you sort of balance the information that you gain from exploring something that has high uncertainty versus exploiting something that you know from past experience to be likely to be high quality. And with backpropagation, it's also a pretty standard update mechanism where you sort of take that reward signal and use it to update the value of all the nodes corresponding to the branch in the model space that you decided to explore. Cool. And just to wrap things up, I sort of want to bring it back to a pretty sort of, and this is a very stylized example, but again, we start with a problem, and this is an allocation type of problem where a farmer tries to decide what crops to plant to maximize their profit. And for a decision like this, you have essentially four components based on our decomposition of the modeling problem. And here, this is an example of one of these steps, and this is the decision variable formulation. And we see here that there are two different ways you can go about it. And one way, and they actually reflect different assumptions. And I want to take a moment here to mention something quite interesting, is that oftentimes, given just an initial description of a problem, it is not actually enough for us to decide what is the correct way to represent something. So here, you have two ways of thinking about it. You can say, okay, the land can be split almost arbitrarily and continuously. And the second way of thinking about it is that there seems to be some sort of divisibility. Like you cannot, there must be some sort of separation between acres of land for different plants. And without additional information, you can say that both of these are actually quite likely. And I can give another example of this, which we've seen in our experiments, which is if you are trying to optimize a machine shop, and you can have a machine that has, say, a constraint, like machine A can produce 20 units of output per unit time. And that can be interpreted in two ways, essentially. One way to think about it is that it is less than or equal to 20 units an hour. And the other way is that it can produce exactly 20 units an hour. And formulating these two things differently can lead to very different sort of outcomes. And the point that I'm trying to make is that oftentimes you have different interpretations given the problem of how a model should be done. And something I'll mention at the end is how we can sort of address this with human AI collaboration. But in the case of purely model exploration, what you would like to see is that all of these equally valid or equally plausible interpretations are all thoroughly explored. And coming back to this example with the farmer and his crops, once you've selected a branch through the model space, then you can say like, now I have a full mathematical model as such. And then there's a translation step that is also done, which goes from the mathematical model to a computer model. And here we're using Groby, but in theory, this can work with any sort of downstream solver. And that wraps up sort of the process. And the example I gave previously was a little bit stylized, and here I've given like a real example taken from the complex OR benchmark. And the point here is that to highlight that some of these problems can get pretty complicated, and the logic can get very involved and entangled very quickly. But in terms of what we use for experiments, we use 4 benchmarks, which have varying degrees of complexity and involve different types of modeling problems. And the metric that we care about is formulation correctness. which is assessed based on whether the model correctly produced the optimal objective as the ground truth. And the first set of results I'll be talking about are these benchmark results. And here, what are called the autoformulator results are basically results obtained by our method. And these four are prior works, which sort of approach autoformulation from different angles. And there's also a fine-tuned LLM that has been specifically and dedicatedly trained on synthetic data that is related to optimization specifically. And we see that in general, as you scale the number of iterations in the multi-color tree search, and as you increase the test time compute budget, like the formulation correctness results do improve, and at least a sort of pretty competitive performance against our baseline methods. Another interesting and complementary sort of insight is that so what we're showing here is that on the x-axis, we have the number of rollouts, so the number of different models, number of unique models that are explored. And on the y-axis, we have the number of unique and correct solutions found on a particular benchmark. And we see sort of that within a few iterations, a lot of the problems has been correctly formulated. But as you ramp up the number of iterations, more and more unique and correct models are found. And that's something that shows that sort of the benefits of exploring diversely, but also unique model formulations. And something else that's quite related is I wanted to highlight just how much redundancy there is in the modeling space. And what this plot is basically showing is that there are along the four components, the percentage of models that are kept after each of the expansion steps. So, if you started off with 10 ways to formulate a decision variable, and after the pruning step and after the rank selection step, where we keep only the meaningful ones, we end up roughly with 5 times less models to consider. And these are the actual models that are explored and evaluated. And this is roughly 5 times across each of the components. So that compounds throughout the modeling process. And another interesting thing that we observed was that if we calculate the entropy in the tree for a particular problem, that the entropy itself is actually correlated with how difficult a problem is. So that's like another useful signal that potentially could be used downstream as some sort of metric of uncertainty or how difficult a problem is. And intuitively, that's just saying for a model that has a lot of different branches, and that also reflects the fact that we are uncertain about how the model should be correctly formulated. Cool. So to wrap things up, I think auto-formulation has the potential to automate and enhance decision intelligence pipelines. And in this work, we mainly focused on mathematical optimization, and you'll see some extensions in a short bit. But throughout most of our experiments, the main limitation that we found was that model verification and evaluation is the crucial bottleneck. So it's a very important future direction to find better ways to evaluate whether a model correctly represents a problem. And of course, another interesting direction is to enhance this with more extensive tool use or some sort of retrieval augmented generation. And going back to what I was saying previously about how to interact with humans efficiently, I wanted to highlight this work that we've also done in the lab, which it looks at exactly this problem. So given that a problem requirement is underspecified or ambiguous, how do you ask the most informative question to the human expert to obtain as much information as you can about competing hypotheses? And lastly, I think progress along the auto-formulation direction will definitely need to be supported by large-scale benchmarks with very diverse problem types and varying degrees of complexity. Cool. So thanks for your attention. And I just wanted to say a big thanks to the Cambridge Center for AI Medicine and all of our partners whose support made this work possible.
Now, we'll be passing the floor to Professor Yuanzhang Xiao.
This is a joint work with Mihaela and 2 other students, Victor and Nicholas, who are also here. So in this work, we're trying to auto-formulate a different kind of decision-making problems that are Markov decision processes. So the motivation is that a lot of decision-making problems are actually sequential. So this happens in uh, various domains like healthcare, logistics, transportation, and telecommunication. So for example, a lot of this system can be modeled as a queuing system, or is a network of queues. So for example, in this hospital example, so patient comes in different departments, right? And then there are existing patients there, so they go into the queue, and then there are resources that are the wards or the beds. And then if the beds are full, then they have to wait in the queue. And then the patients get served, and then they are discharged. So some apartment may share a common wards. So these beds are allocated among different departments. And also, I mean, this scenario is a case where there's a no tandem of queues. That is, each department are, I mean, all the departments are parallel. But there are also cases where these connections, there are connections between the different departments, where the patients goes into one department and then go to the next and so on. So this is a tandem of queues. So here the difference from a mathematical optimization problem is that so the patients are arriving and departing the system, and we have to make decisions each time there's a patient arrival and departure, right? And also our decision will affect the state of the system, right? If we consider state as the number of patients in each queue, and then that affect the future performance of the system. So we have to make a decision over time, and the decision also affect the future. So so in this case, our solution, right, will be a policy that is depending on what are the current queuing status in the system. We have to decide whether we admit or reject the patient. Okay, so this is a sequential decision-making problem, and a very common tool to model this or to solve this is the Markov decision process. And then in terms of auto-formulation, we talk about optimization, right? And there's a cute or there's a common consensus that once formulation is done, solving is almost technology. So there are various solvers to solve the problem efficiently. But in contrast, for the MDPs, solving the problem is another challenge, right? Because of the curse of dimensionality. So if we have multiple queues, and then basically the state space grows exponentially with the number of queues in the context of queuing systems. So solving is also hard. I think that is one of the biggest difference from auto-formulating optimization problems. And that's also a challenge we want to address when we auto-formulate MDPs. So we try to alleviate this computational challenge in the auto-formulation phase, before solving it. So there are some methods in reducing the computational complexity, but those are orthogonal to our work. So we can actually, our work is also complementary. So we wanna alleviate this problem in the prior to solving the problem. Okay, so to summarize, what are the challenges for auto-formulating MDPs? So there is formulation challenges, right? For example, some similar challenges as formulating the optimization problems. And also, I think here, there are more types of components in the model. So we have states, that is the number of patients in each queue, and actions. And also we need to formulate the system dynamics. So based on how often patients of certain type comes and go, right? And there are also some implicit constraints. For example, the action set, the feasible action set may be state dependent, right? So so whether do we admit or reject a patient may also depends on the queues, right? If the queue is full or not. The second challenge is the computational challenge. That's the one we have talked about. And then finally, there's an interpretability challenge, which is the policies are inherently harder to interpret than the decision variables, right? So if we have a optimization problem where we get the optimal solution that tells us the optimal allocations, it seems easier to interpret. But if you have a policy, usually these policies are described in terms of a lookup table. We have a state and then the policy of 0 ones. So just looking at a large table, it, it's harder to get a sense of the meaning of the policy. Okay, so we're trying to find the structural results of the policies where we can say maybe this policy is a threshold policy. You just look at the current queues, and if it is above certain threshold, right, the occupancy is above certain threshold, we do not admit. And if it's below the threshold, we admit, right? So if we can have these type of structures for the policy, if you can identify those structures, then we can also come up with an explanation for the policy, which makes the policies easier to be implemented and adopted. Okay, so then to address those challenges, I want to summarize the contributions. The first is that this is the first auto-formulation for the sequential decision problems. Right? So there are a few works on mathematical optimization problems, but those are for like more static decision-making problems. And the key here is that we actually have used a concept of operator graph, which we will describe in the next slide. That actually greatly increased accuracy and interpretability of our method. And then in terms of theory, we have we prove some theoretical results about the existence of universal graph topology. So that actually greatly reduced the search space. So it makes the auto-formulation process more efficient. And then in terms of methodology, we use the same LLM plus MCTS framework as a auto-formulating optimization work. And then we kind of also tailored this method specifically for the MDP problems. Okay, and then empirically, we have a high accuracy on the data sets that we curated. So let's delve into some more details, right? So you can look at one example. This example considers a hospital with 2 wards one for the critical patients, and one for the general patients. Okay, so there are two queues, but they share one bed. I mean, they share a certain number of beds, right? So they are connected. They are not completely separate systems. And then we have a description of, on average, how many critical and general patients arrive each day, and then the service time of each type of patient. And then on each arrival, we have to decide whether do we admit or deny the patient, right? And denying occurs different costs for different patients. And also for each patient that's currently in the system, there's a holding cost, right? Because there are resources allocated to these patients. So our goal is to minimize the long-term discounted cost of the system. So this type of queuing system can be modeled as an MDP, and the way to solve it is to solve the Bellman equation. So the Bellman equation is basically, it looks complicated, but this V star is the value of a state. So X here is the state, right? So we can think about this as queuing status. Okay, the number of patients, the number of critical and general patients. So vector of 2. So for each possible state, we need to solve for the value, which is the total cost starting from this state, right? And then this can be, so the values, there is a Bellman equation that links the values. Okay, so the optimal value should satisfy this Bellman equation. And there's usually an iterative method to solve these Bellman equations. And once we get the values, we can get the optimal policy from the values. Okay, so now if you look at this equation, we can identify some key parts of this equation. So the first one is the cost. So this is related to the holding cost, this rho h, the holding cost, and it's proportional to the number of critical patients plus the number of general patients, right? And then another key component is related to the state transitions. So basically, these lambdas are the arrival rates and mu's are the departure rates, right? So these arrival and departure rates, they indicate the state transitions. And finally, there is also events and action involved here. So after each arrival, depending on whether we admit or deny the patients, the state goes to the so it goes to a new state, right? And then there will be the value of the new states here. So these three components, once we identify these, we can also write the Bellman equations in terms of operators, because this one equation can be considered as a composition of multiple equations, and each equation is a smaller equation, I mean a smaller atomic function that corresponds to the cost or the state transition or the events of arrival and departures. Okay, and we can view this as an operator graph. Okay, so in our formulation, if you look at this set of operator graphs here on the right-hand side, we can so it can have different topologies. So how we write the equation can be mapped into these type of graphs, right? So in the previous example, we have operators related to the events, right? And then after that, the next level is what we call uniformization operator, which is these state transitions marked in blue. And then after that is the cost operator that's related to a cost. So then we can link this composition of atomic functions in terms of these graphs, right? So in general, this graph can have many different topologies, right? But our theoretical result is that there exists a universal topology. That is, first, we have the events operators, and then the next level is the uniformization, and then the cost. So this type of graph can all the Bellman equations can be written in this form. So that's an important result because that means when we search for the correct operator graph representation of the Bellman equation, we can fix the topology, right? So we only look at the different components here. So that greatly reduces the search space. And another okay, and then to address the computational challenge, what we do is once we get the operator graph, we have an algorithm that identifies the structures of the optimal policy. So we can say this optimal policy should be monotone. So the action is increasing or decreasing with the state, or it's a threshold policy. And therefore, in the solution phase, instead of search this entire big set of all feasible policies, we can either go to a smaller set where we have monotone policies or threshold policies. So therefore, before we solve the problem, if we can identify the structures, we can call a specialized server, specialized solvers that actually search in a much smaller space. So that's how we deal with the computational challenge. And also these structures will improve the interpretability of the policies as we discussed earlier. Okay, so for the MCTS process, we kind of tailor the MCTS for the MTP problems, where one thing is we do a syntax check before we go to the final level and put the model into the server. So we will stop the process at some intermediate levels. And then also we, in addition to the LLM self-evaluation of the formulation, we also look at the solver convergence and use that as a signal. So that gives a better reward. And then we test this on a data set of queuing problems with different event types and in different applications. And we compare with some benchmarks. Like just ask the GPT with a single prompt, or use the chain of thought, or we have targeted prompts similar to the MCTS. So basically, the main conclusion is that we have the best accuracy, and also the MCTS, the tailored MCTS, syntax check and solver feedback actually improve the accuracy a lot. So in summary, this is the first auto-formulation for sequential decision-making problems. And by using an operator series-driven auto-formulation, we increase the accuracy because we have the test to operator mapping that narrow the hypothesis. And it improved the interpretability both for the models, because the test to operator mapping ties the model parts to the natural language descriptions, and also improve the interpretability of the policy because we identify the structural results.
Definitely. Thank you so much, Yuanzhang, for a fantastic talk. We have two amazing panelists today. We've got Professor Radek. He is the Director of Computational Health and Medicine Initiatives at the Texas Advanced Computing Center at the University of Texas at Austin, as well as he is a trained doctor, academic physician, and scientist. And following on, we've got Professor Stefan Scholtes, who is a Dennis Gillings Professor of Health Management, Director of the Center for Health Leadership and Enterprise at the Cambridge Judge Business School, and his research is divided into three main streams: primary care at scale, healthcare utilities, and Center for Global Healthcare Convergence. So I welcome both our panelists to the floor, and also Professor Mihaela van der Schaar to moderate.
Thank you so much, Radek and Stefan, for being here. What a pleasure for me to have the chance to talk to you about this. So first question to both of you, what do you think? Do you think that we need, in the type of settings that both of you do, so you are not only academics, you also have a very clear understanding of the needs, definitely in healthcare, in terms of support, analytic support, operational support, logistics support. Could we use such autoformalism tools to improve delivery of healthcare in hospitals and clinics? And if not, are there, or if not, or if yes, are there specific areas where such tools should be specially developed and become useful? Stefan, I'll start with you.
Okay, thanks, Mihaela. Thanks for inviting me. It's great to be with you. Lovely group of people here. So I'll start with a story. Last week, so I happen to be chair of the board of a very large primary care practice here in Cambridge, 60,000 patients and around about 30 doctors. And we have our doctors are either duty doctors, they look after urgent patients with urgent needs, or they do continuity of care work. And for those who are duty doctors, we need to decide, we have 5 sites, and we need to decide how many doctors we need in each site for duty care. And at the last board meeting, we reviewed how we're doing, and we're doing very poorly. There's a lot of variation around the load of the doctors in the sites and so on. So we should be doing better. So this is a clear optimization challenge. We have a relatively good understanding of and can forecast, let's say over the next 2 weeks or so, how many urgent care patients we need, and that depends on the site. It depends on how many sick kids you have, because something is going around in the schools and so on. And we also know pretty much which doctors we have. And we have bought software to help us. And we have a rota lady who is fantastic. She's been doing the job for a long time, and it's a very tough job. So I asked her, so Louise, how's the software? And she said, it's rubbish. I can't use it. It just doesn't work for me because it's way too inflexible. I mean, it sort of puts me into a straitjacket that doesn't work at all for our context. And I think that's a general theme that you often see, that off-the-shelf, boxed-in software doesn't work. So what I hear from you now is this is an opportunity for Louise to not interact with the software and have one fixed set of constraints that she needs to specify and so on, but can basically be flexible in the kind of constraints she has. And she doesn't even have to specifically formulate them in a particular way. She can formulate the constraint in natural language. Oh, Fiona won't be around on Wednesday, kind of constraint. And that would be so much better. So if we could do that, I think I'll let Radek respond to a couple of these things as well in a minute. I think there are 2 things that we have here. We have two hurdles to using optimization in certainly in the operational space. The first is the off-the-shelf solvers are too inflexible. The second is clinicians and also the administrators hate to be told what the optimal solution is. If they're able to work out the optimal solution with an LLM, then it's a co-owned, co-created solution. I think it might be that this is a much easier way for them to accept the solution, because they can begin to defend the solution. Otherwise, they're presented with a solution, and if it's not a good solution in the end, they can only say, well, the software gave me this. So I'll stop here, Mihaela. Does that
amazing, amazing, Stefan. Thank you so much. Radek.
Yeah, I mean, I couldn't agree more. It seems to be like, my 39 years of practice was basically at failing of to optimize the system, because essentially that's what we were doing, scheduling patients. The problem is, of course, that this is not only number of patients, but what kind of patients and so on. But so I will completely agree with this. You ask if it is useful. Absolutely, yes. I think actually this approach, which is dynamic. So basically, it's not a single snapshot optimization, but it's a dynamic one, which you have the progressive optimization with each state. I think this is really a very substantial move in the right direction and could be very helpful. Of course, implementation will depend on many other things. But I think one of the things that I have in my experience, and I think you will probably agree with me, because it is quite obvious. Important thing it is that we are optimizing usually just current state. We are optimizing one system, in other words. So, and I think that what we are optimizing, it depends on who is deciding about those things. So, in America, the hospitals are deciding about what's going to be optimized. So optimized is going to be dollars. That means, more patients, shorter period of time. And of course, that's not optimal for doctors, patients. So that, that I think what will be, I don't know if it's possible. This is a question, I guess, to all of you. I think this was wonderfully done. I was already very excited when I heard it on Monday, the first part of it. The question would be, is it possible to inject into this Bellman's optimization worst case scenarios, for example? So not only the minimization, but also maybe min-max optimization, or maybe even a distribution of uncertainty. So basically to model the robustness of a system. And if that's possible, perhaps this would be even more wonderful if one could model resilience. So basically design an agent with additional variable, which would be health of a system that takes under consideration, which will allow it to also learn, to adapt. Because I think the problem is that I personally think that the main problem is over-optimization. All the systems, I don't know if Professor Scholtes agrees with this, but I think in business as well as in medicine, although it's very similar, it's always the same thing. We over-optimize the system, and then something goes wrong, and we are surprised that we have financial crisis, or something collapses, and we suddenly have so many services in hospital that don't work, or that we have 50 patients waiting because we spent too much time with the one in the beginning, and there was no recovery system, no redundancies built in. So that's basically kind of a food for thought. But in my mind, these are the robustness and the resilience would be the most important things to build in such a dynamic optimization system.
Thank you so much, Radek and Stefan. Both of you gave us a lot of food for thought. Of course, some of this is still optimization, some of still is Markov decision processes, and is not a learning process. We don't make assumptions about how good is the estimation that, like Stefan has said, of what will happen in the next week or 2 weeks, and bringing this learning aspect into the autoformalism agenda is something that we are actively looking at. I don't know whether Yuanzhang and Tennison, you want to comment on that, or you just want to take it on board.
So, Mihaela, I have one other comment.
Yes, maybe we should take your comment and we can let Yuanzhang and Tennison respond at the very end.
Yeah, which is
Thank you.
it's very simple. So we tend to think about we need optimization models to get to an optimal solution. Now, do we? I'm not so sure. So, when you have what Louise, my rota person, would struggle with is tell you what the constraints are. But she wouldn't struggle with if you gave her a solution to say whether it's a feasible solution, and if it's not feasible, why not? So, you don't actually need, she doesn't need a model. She only needs a solution. So is there a way of sort of being iterative in that sense that
Brilliant, yeah,
you don't
absolutely
need to
brilliant.
specify
Yeah.
the model for me. Just give me a solution and guarantee to me that it's optimal, and I tell you whether
Robust, optimal, maybe guarantee to me that's robust, like Radek said.
Yeah, exactly.
Wow, this is really wonderful. Marika, thank you so much, Stefan and Radek, for this. Marika, there are probably questions from the audience to both the panelists and the speakers. I'll let it in your hands. Thanks a lot, Radek and Stefan.
Great. Thank you so much for both of your insights. If we do have any questions, we'll be taking maybe one quick question, but you'll have to put them on our Slack channel. If not, we'll be wrapping up the session. And I would just like to say a huge thank you to all of our speakers and panelists for the insights today, and for everyone who joined us to celebrate our 50th session, inspiration exchange session. If you do have any further questions to our speakers earlier, Tennison or Yuanzhang, they would be happy to answer any questions offline on over on Slack as well. And the only other thing would be the next session will be held on the 24th of November, and we will cover the NeurIPS highlights from the lab, joined by our industry collaborators. And I think before we do finish, Stefan or Radek, would you like to say any final words about autoformalism, or any final phrases that you'd like to share?
I think this is fascinating stuff, guys. Carry on working on it. This puts optimization in the hands of people who would otherwise not be able to use this stuff. I think that's absolutely good. So carry on.
Cannot agree more. Please continue. This is very interesting, and I think it's very promising. Again, I want you to think about this resilience and robustness, because I think that's something that I think we are failing in from medicine to economy and to anything else. But I really would like it to see and develop further. Thank you for having me.
Amazing. Thank you to you both. Yuanzhang, anything you would like to say?
No, I just want to thank you for all the great comments. I think they are really important directions for us to work on.
Fantastic. Well, thank you so much. And I think that brings us to a close today. The recording for the session will be available soon on our YouTube channel if you'd like to revisit the session, or if you would like to share the word about our engagement session to your colleagues or your friends. And with that, we hope you have a nice evening, and we hope to see you at our next session. Thank you for joining us today.